In this series, we're going to take a look at two more types of first-order differential equations, pretty common ones, one of which is going to be called a linear first-order differential, and the other one is going to be called an exact equation. A first-order linear differential is one that has a particular form, and the particular form is that you can isolate dy dx. You have a function of x times y, just y, not e to the y, not sine y, not square root of y, just y, is equal to a different function of x, or the independent variable. Now, the technique to be able to solve these is actually pretty easy, because what we're going to do is we're going to multiply that by something called an integration factor. And the integration factor essentially allows the problem to become much more simplistic when we multiply through. I'm going to define the integration factor for a linear differential equation to be e to the integral of p of x dx. Sometimes we call that I as the integration factor, so that's going to be e to the integral of p of x dx. So if I say I throughout the video, I is not the imaginary unit, I is just going to represent the integration factor. We're going to multiply everything on both sides by the integration factor, and we're going to get this horrific looking expression. And one might be wondering, well, why would we do that? Because now it looks much worse than when we started. However, right here, what I put in the box, that's actually the result of a product rule. And so what we could do is we could go backwards from the product rule, all right? And if you really wanted to, you could note it as integration by parts. And what you'll notice is that that could be represented as the derivative with respect to x of y(e) to the integral of p of x dx. So basically, all we're going to do is we're just going to say y times the integration factor I is equal to q of x e to the integral p of x. We're going to integrate both sides to eliminate this dx. All right, so this is going to go away. And then finally, we can just divide both sides to solve for y by this integration factor. And so there's two ways to write the formula, if you would. Now it's a formula, but it's actually much more than a formula. So you could write it as y equals 1 over e to the integral of p of x dx times the integral of qx e to the integral px dx plus c. Or if you think of this as I and this is I, you could just write this as y equals 1 over the integration factor times the integral of q of x times I dx plus some constant of integration c. That might be a little bit easier for us as we go along. All right, so this is the derivation of the formula that we're going to use to solve these linear differential equations. It's actually pretty easy to do that. All right, so we're going to look at a number of examples to where all we're going to do is solve initial value problems that are linear. And in the first one, what I'll probably do is I'll probably plot it for you, and then I can show you both the slope field as well as the particular solution on the same graph, just like we did before for some of the separable equations. So as a first example, we're going to find the general solution and the particular solution to this differential equation. We're going to plot the slope field and the particular solution on the same graph. All right, so let's first of all start by always putting this into the form of a linear differential equation. And we're going to go ahead and start by solving that for dy dx. So we're going to rewrite this as dy dx plus 1 over xy equals x squared. And what we notice is that now y has a coefficient of 1 over x, and that's going to be our p of x function that we just defined above. And we have a q of x function, which is just going to be x squared. Right. Now we're going to plug this into our formula. All right, so all the stuff that we did up here, that was just the derivation of the formula. it might be helpful for us to find what I is. So we could just substitute it immediately into the formula. Now remember, I is equal to e to the integral of p of x dx. In this case, that's e to the integral of 1 over x dx, which is the same as e to the ln. Now technically, it's the absolute value, all right? But if you look at the initial value, y at 1 equals 3, there's no need for us to consider the absolute value because 3 is always greater than 0, all right? So it's going to be e to the natural log of x, and we know e to the ln of x is just x. So this is a really nice and easy integration factor for this problem. All right, our formula, and I'm going to write it out just because it's the first time. Y equals 1 over I times the integral of q of x times I dx plus c. We're going to substitute. Y equals 1 over x, because I is equal to x. Integral of q of x, so remember q of x is x squared, times I, which is x dx plus c. And now it becomes really easy. We're going to multiply these out. So we have 1 over x, integral of x cubed dx plus c. The integration, extremely easy, 1/4 x cubed. So y is equal to 1 over x times 1/4, excuse me, not x cubed, x to the 4th plus c. And then our general solution, if we were to distribute the 1 over x, is going to be y equals 1/4. We're going to subtract 1 from the exponent. And we can't forget that we have to divide c by x as well. All right? So we end up with this 1/4 x cubed plus c over x. And that's going to be our general solution. Now remember, we had a particular solution. Y at 1 is 3. Right. And we're just going to substitute 3 in for y, 1 in for x, as we've done a number of times. So 3 equals 1/4 times 1 cubed plus c over 1. 3 equals a 4th plus c, which implies that this becomes 12 fourths. 12 fourths minus 1/4 is 11 fourths equals c. And there's two ways to write the answer. We can get y is equal to 1/4 x cubed plus 11 over 4 over x, or another way to write it, although it's lipstick on a pig at this point, it's not going to make it any prettier, 1/4 x cubed plus 11 over 4x. Either of those solutions, just as good algebraically. The last thing we'd like to do is we'd like to make sure that the solution makes sense by plotting it both as a slope field, and then we also want to plot the particular solution. So we go to our Desmos. I'm going to import the graphic. I'm going to expand it, and I'm going to explain really quickly what's going on. All right. So here's our graph. And I did, just to verify, I took that point, that movable point, and just traced it over. And it certainly looks like it fits, so I don't have any problem with the validity of the solution. What I do have problem with is looking at the solution and noticing that there's this sort of auxiliary solution that's going on here. Remember at the top, when we did the integration factor, that technically this should have been absolute value of x, but we didn't care. And that was because of the initial value. So this extraneous solution right here, we don't need it because it's not part of the initial value. Remember, the initial value was 1, 3, okay, which seems like it's actually this vertex right about here, or maybe like this slope right there. And so since 1, 3 does not exist on, so we know that 1, 3 is not an element of this graph, then we don't even care about that. The only curve that we care about is going to be this curve over here. So just making sure that when you guys see the solution that you're able to interpret what's going on with this. Right. So in the next video, what we're going to do is we're just going to solve a few more of these linear differentials. I'm going to show you some of the techniques to be able to solve these. We're not going to graph them, nor are we going to show what the slope field looks like. So we're just going to get the solutions, although you should always check by using the geometric solution to it as well to verify your analytic solution.